and welcome to the 2025 IEEE Vision, Innovation, and Challenges Summit. I'm Glenn Zorpet of IEEE Spectrum Magazine, and I'm pleased to have here with me today Kamal Sarabandi, who is the winner of the 2025 Dennis J. Pickard Medal for Radar Technologies and Applications. Dr. Sarabandi is the Fawaz T. Ulabi Distinguished Professor of Electrical and Computer Engineering at the University of Michigan in Ann Arbor. Dr. Sarabandi, your specialty has been in the application of radar in remote sensing, and in particular, you advanced the use of a technique called radar polarimetry to in these applications for remote sensing, in particular for weather and climate related applications. So in radar polarimetry, you preserve and analyze the effects on the polarization of the signal in effect. So this is a specific area of radar technology that's been advancing. How did you get interested in this as a young engineer?
Very good. Glenn, first of all, thank you very much for this interview. It's really a pleasure to be here. Well, going back to your question, I became a graduate student in 1984, University of Michigan. I was interested in high-frequency applications, electromagnetics, applied electromagnetics in general, and I was searching for a PhD topic to work on. From the onset, I was, very much interested in working on something that would be a lot more impactful rather than working on a specific radar component or a subsystem and things like that. And at the time, I remember this issue of global warming was being discussed, and I wanted to see how I can participate in a research like that, and wanted to do something along the way to help humanity as a whole, and was interested in a bigger picture type of problems. And this presented to me as a very interesting research topic to work on something like that people hadn't tried before. And I started looking into application of radar in evaluating basically different processes that affects the Earth and life on Earth.
So radar polarimetry goes all the way back to the 1940s, but it didn't really start being used in sort of a practical way until the 1970s. Which coincides with your undergraduate years. Were you aware of this at all?
No, actually, I was not very much aware of that. My entrance at University of Michigan at the time coincided with Professor Ulabi, my professorship named after him. He was my mentor there, and he started radar remote sensing of environment at University of Michigan, and I joined his group at the time. Problems of radar remote sensing of environment is an underdefined problem in a sense that the number of parameters that influence what radar measures far exceeds than the number of parameters that radar can collect.
So a major breakthrough in this era being the 1980s, was the application of dual polarization radars. What is dual polarization in this context, and why was it such a big advance for weather radars?
Sure. So polarization, basically, electric field can assume any direction, right? You could have vertical polarization, you can have horizontal polarization. The radar can transmit vertical polarization, but when it hits the target, what comes back can have combination of vertical and horizontal. Therefore, you're sending one signal, you're retrieving two back, and next time you can transmit horizontal polarization and again receive V and H back, and therefore you can form a matrix. So you're in effect collecting three independent parameters when you go to radar polarimetry, and polarization basically is referring to the direction of electric field. I can give you one example maybe to make it a little bit more clear. If you look at, pine trees, pine trees have this very special shape. Actually, through some modeling effort, we were able to model these things mathematically in a very, very compact form. And I can come back and tell you a little bit about the inversion process, trying to sort of combine all these parameters into some basic roots and then get back at what target you are observing. So coming back to the polarization, the specific direction of the branches or the pine needles that are coming off of the tree, these are very polarization specific. So if you have a horizontal branch and you send a horizontal polarization, you get more backscatter. Whereas if you were to send a vertical polarization for those twigs and branches, you would get less response. And combining these different information allows you to say or discriminate different species of the trees. So you could have a mixed stand or you could have a specific forest stand, and you can use polarization to sort of probe, what directions are the branches, what directions are the needles, and things like that.
In the 1990s, you had a major breakthrough in radar technology, which led to a paper, Derivation of Phase Statistics from the Muller Matrix. And you were building upon research in optics by Hans Muller in the 1940s. So this paper of yours is one of the really milestone papers in the history of radar, especially in that era. Can you explain in simple, everyday terms what it was you achieved in that paper?
Yes. So as I mentioned, radar, polarimetric radar, can measure scattering matrix of the target. We said we can send vertical polarization, receive V and H. That's two columns of the two components of the scattering matrix. You can send H, receive VH. That's the other two. So you have four components of the scattering matrix. People up to then were only looking at the magnitude of the elements of that scattering matrix. That the scattering matrix by itself is a complex number. There is a magnitude and phase associated with each component of that scattering matrix, right? And people were always looking at the magnitude of SVV, SHH, and SHV. These are the copole and crosspole components. People didn't pay too much attention to the phase difference between V and HH or VV and HV. We wanted to exploit that component as well, right? The measurement of phase by itself is a very complex process. So a lot of time, people can measure, for example, when you increase the frequency, you go to optical frequency or even at microwave frequency, we can measure Stokes matrix. These are all power measurement. This paper specifically went and said, okay, if I have just power measurement of these Stokes vectors, can I go back and retrieve the phase? So from only power measurement, how do we go back to phase? Because when you come back to phase, now you're going at the fundamentals of, what component of that the scattering matrix phase I can relate that to the target. And that paper talked about that and unraveled this mystery basically to go back directly just from even power measurements, SVV, SHH conjugate, ensemble average type, to come back and get, okay, what is the phase difference statistics? And it turned out that you can very nicely model this, and it fits a beautiful model. Einstein said that if your result is simple and beautiful, you know that you have the correct answer. And that was the case.
So polarimetric techniques were applied early on with synthetic aperture radars. These allowed monitoring wide swaths of Earth's surface for characteristics important for studying agriculture, weather, and climate, and so on. So what were some of the memorable milestones of this research in that era?
Yes. So, during the time, I was working on this NASA JPL team was also working on launching shuttle radar imaging, SIR-C, they called it. And this was the C series. We had SIR-A, SIR-B, and SIR-C. SIR-C was a 3-frequency radar system. And this was the first time that we were able to apply a lot of these techniques, not only the forward model that we developed for vegetation, croplands, bare soil surfaces, to measure soil moisture, surface roughness, vegetation, biomass. That data was very critical to really put in practice a lot of theories that was developed at that time. And we were able to
Theories about climate change or?
That was about climate change. We used it to measure, for example, some very key parameters of vegetation, above ground biomass, below ground biomass, classification of different types of, tree types and things like that, to really map, how much biomass, how much photosynthesis takes place. Radar was promising that a technology that we could observe the entire global carbon cycle with a snapshot. This is a connected system, right? The earth is connected. You can go to a forest, you can do all these measurements, but that doesn't give you anything. You have to be able to measure the whole surface of the earth, wherever you have forests, wherever you have croplands, to be able to connect these things. We wanted to measure how much biomass is being generated, what is the leaf area index, how much area of leaf area exists, because that was connected to the photosynthesis. How much carbon dioxide vegetation are capable of extracting from the atmosphere. Carbon dioxide is important because it's one of the important greenhouse gases that keeps the temperature of the earth, high during the day and night. The difference is low. It's a good thing. These greenhouse gases is actually what allows life to persist on the planet, because it moderates the temperature. But the thing is that too much of a good thing can be bad thing, and that was the reason, through human activities, industrialization, burning fossil fuels, we were generating too much, or we are still generating too much carbon dioxide and releasing those, uncontrollably into the atmosphere, and that's why the temperature of the planet is rising. So we wanted it to be able to at least connect these two pieces together.
Right.
Yeah.
So starting in the 1990s, after your work and your discoveries, you and your colleagues at Michigan began investigating many uses of radar polarimetry in different fields. When you think back on that period, what were some of the most exciting or interesting for you, some of the applications?
Yes, so we started looking into, wide range of application of radar polarimetry. Remote sensing as a whole is not confined necessarily to one particular application. The fact that electromagnetic wave can penetrate through vegetation, for example, it can penetrate through your clothing, right? So one of the research we applied these techniques was standoff detection of concealed weapons. During Columbine high school shooting and stuff like that, people were paying attention to how do we monitor people, carrying guns. So we started looking into that problem, and we wanted to develop a system. This is an ongoing research, by the way, because of this special nature of electromagnetic wave at lower frequency that can penetrate clothing and stuff like that. We use radar polarimetry. Without imaging the person, we could detect, whether that person coming from 100 yards away, whether he's carrying something other than, the body, for example.
Enormously useful.
Very useful, right? It has both homeland security application. It has security applications for stadiums, wherever, you have a large population, those techniques can be used. So that's one. The other one, we applied a lot of these techniques to automotive. Automotive radars now are commonplace. We started a similar research late in 1990s, the use of millimeter wave radar, polarimetric radar for autonomous vehicles. And we had, collaboration with General Motors at the time to develop these very advanced radars. So we use radar polarimetry to develop a sensor, for example, to look at the road and tell you what type of surface your car is driving on. Is it wet asphalt? Is it dry asphalt? Is it concrete? Is it gravel? Can I detect black ice? Can I detect standing water without the use of driver? Because now, you have eyes, you're driving your vehicle, and you have a supercomputer behind this sensor that can, based on your past experience, really tell what is going on. Cameras cannot do that. If you see a black spot on the ground, you don't know whether this is a shadow or it's a standing water or it's a black ice or whatever, right? We wanted to have this multi-sensor techniques for autonomous vehicles. So we developed that sensor, for example. at that time, and that this simple radar sensor can look at the ground and tells you what type of surface the car is driving. In addition to safety issue, there are also issues related to, for example, the knowledge of vehicle traction on the road can assist the car to maneuver better, right? Can I slam on the brake if there is something? If it is slippery, you don't want to slam on the brake, right? So all those important information can be retrieved from these radar polarimetry techniques.
Do you know if these techniques are being used in any autonomous cars or research programs?
So as of today, some of these things, I'm not aware of whether that specific sensor is being on cars or not, but I am sure that these things will go on cars because the current technology is not sufficient, even after all these investments with a lot of money poured into it. We haven't reached yet to that initial optimism of creating autonomous vehicle because of two factors. One, whenever you have a system that is supposed to do autonomy, there are two parameters that you have to basically pay attention to. One is probability of detection. If there is an obstacle on the road, if there is a vehicle that may come across and go into your lane, you want to be able to detect that with a probability of 0.999999, right? Very small amount of error you want there. So you can increase that, to make sure that you really achieve that probability of detection. But the problem is that you could also have false alarm rate, right? So if there was nothing, your sensors, if you have too many of these sensors and then they're doing a lot of measurements, then one of those sensors can send a false, signal back, and then all of a sudden your car slams on the brake for no good reason. You don't want that either, right? So you have to have very, very low false alarm rate and very, very high probability of detection. And then gradually they become adapted, as the need comes up, as, people try initially to go with the smaller, more understandable technology like cameras we are all very familiar with, right? Because it's part of our experience every day, vision, right? But you can go so far with vision. There are certain things that your vision is not sufficient. And to increase the probability of detection, lowering the false alarm, you have to resort to other technologies, such as, this type of radars.
Terrific. Professor Sarabandi, thank you so much for joining us, and congratulations on winning the Dennis J. Picard Medal.
Thank you so much. It was a pleasure being here and talking to you.